Okay, the first question on the problems I gave people to work at the beginning of class, you were given an object with initial velocity 3.5 meters per second, final velocity of 7.5 meters per second, displaced 55 centimeters, and you were asked what its acceleration is. Okay, well, you set that up. You have the equations of motion. You should understand the equations of motion. You should know how to derive this equation and this equation by integrating, starting with the assumption of uniform acceleration. And then how to eliminate t from the two equations. Solve this equation for t, plug it in here, you get this equation. Solve this equation for a and plug it in here, you get this equation. Okay, these equations are totally useful. We use this third equation. Now you have an alternative. You have this information. You plug this information into this equation and into this equation, and then solve the two equations simultaneously. You can find the acceleration. You can do that. It's a useful exercise, and it'll motivate you to understand that if you just eliminate t between these two equations, you get a single equation that you can solve for the acceleration. So these two equations are fundamental. These two equations are ancillary. Now this equation could be regarded as fundamental because you can conclude it very easily from the linearity of the velocity versus time when the acceleration is constant. It follows then that the average velocity is initial plus final velocity divided by 2. Average the initial and final velocities, multiply that by t, you get your displacement. So this equation is fundamental in that sense. But we're going to take these two equations as fundamental in this course. This equation should be very easy to understand in terms of what I just said. Okay, anyhow, having identified these three things, this equation, if you declare x naught to be 0, which you can always do as long as you haven't declared another related x naught, you see that this equation has only one remaining unknown, which is the acceleration, and you can solve for it. So we solve for the acceleration, we get this, plug the numbers in, we're going to get 0.4 meters per second squared. Now intuitively, and that fourth equation up there is intuitive, we're not even using the equation, we're just using the idea that acceleration is constant, so the average velocity is the average of the initial and final velocities. This comes about because if acceleration is constant, the velocity versus time graph is linear, and on a linear graph, the average of the quantity between any 2 points on the graph is the average of the initial and final quantities. Okay, just because of linearity and just basic geometry, which nobody knows. Okay, so we have average velocity is this. So you know how far you go, you know your average velocity, divide it out, determine it's going to take 10 seconds. And then acceleration, change in velocity over change in time, 4 meters per second over 10 seconds, gives you the same result you get from the equations that don't involve any understanding, okay? So I always encourage you to work from definitions and basic properties of linear graphs, okay? But in most cases you can do that, not always. Second problem involved angular motion, where you're accelerating uniformly from 2 to 5 radians per second. So you'd have your omega naught and your omega f as you go through 2 revolutions. Well, if you want to do equations, this can be reasoned out in very much the same way this was, but we want to illustrate the equations. This equation is totally analogous to this equation. Instead of acceleration, you've got angular acceleration. Instead of velocity, you've got angular velocity. Instead of position along an axis, you've got angular position. Immediate translation. the equations that govern uniformly accelerated motion are derived exactly the same as these are, with the initial assumption of uniform angular acceleration alpha. You just integrate again. You get exactly the same equations, but with the angular symbols. Anyhow, you plug the information in and you get your result. And I estimate it's 0.9 radians per second squared. Did it in my head, so don't believe it. Verify it. Okay. Next problem. What were you given? You're given that the change in kinetic energy is 8 joules, and you were given, I believe, an initial velocity. Yeah, okay. An initial velocity of 2 meters per second, and work done on the object equal to 8 joules. So your change in kinetic energy is 8 joules. The work done by the net force on the object is equal to change in kinetic energy. So that's going to be equal to 8 joules, and of course that's the final kinetic energy minus the initial. Now, I probably would have been better to leave the delta W net on here instead of the 8 joules until I plugged in the numbers, solve everything first, but I did what I did, and it comes out the same. Okay, so final minus initial kinetic energy is 8 joules, so the final is 8 joules plus the initial. So 1/2 m Vf squared is 8 joules plus 1/2 m V naught squared. Well, we multiply by 2 over m. We get Vf squared is 2 over m times 8 joules. Times the quantity, well, this quantity, 2 over m times this side. I don't need to read it to you. We notice that the 2 over m will multiply the 1/2 m here, leaving you just V naught squared on the end. And the 2 over m is 2 over 2 kilograms, because the mass given was 2 kilograms, times your 8 joules, which is 8 kilogram meter squared per second squared. You've got to understand those units. Kilograms divide out, and you end up with 8 meters squared per second squared plus 4 meters squared per second squared, and etc. You end up with Vf squared equals 12 meters squared per second squared. The square root of 12 is about 3.5, just a little less. And the square root of meters squared per second squared is meters. You end up with something about 3.5 meters per second. So again, well, you read the problem, see what we're given. This is how it can be set up. Okay, here we have an object displacing down an incline, sliding down an incline without friction, rolling, whichever. There's no friction, so it's going to be the same either way. So what do we have? We have a 30-degree incline. Now the problem, as stated, was a 37-degree incline. I kind of accidentally used 30 degrees. It's very convenient, but 37 degrees would have been okay too. And you should work it out with 37 degrees. Okay. We're going to use potential energy, or at least the idea of potential energy. We have a downward displacement of 10 meters. Now we have a 20-meter displacement in this direction, but the displacement in the downward direction is 10 meters. If we multiply the displacement in the downward direction by the gravitational force, which is downward, we find that gravity does 980 joules of work on the object. It displaces 10 meters in the negative direction. Gravity exerts, this is a 10 kilogram mass, that's in the problem, so we assume you have that, but a 10 kilogram mass will experience a force of 98 newtons due to gravity. And you multiply the 98 newtons of gravitational force by the 10 meters of downward displacement, you get the work done by gravity. You could also calculate the component of the gravitational force parallel to the incline and multiply that by your 20 meters, and you would get the work done by gravity, and you get the same thing. There's no friction. Gravity is the only, well, the gravitational force one way or another is the net force acting on the object. Okay. So, you find that your kinetic energy change is the work done by the net force, which is a gravitational force on the system, 980 joules. Your change in potential energy is equal and opposite to the work done by gravity on the object. Okay, and that is negative 980 joules, because gravity does 980 joules of work. Equal and opposite to that is negative 980 joules. Okay, now that is understood. If we have this object up here and we were to drop it 10 meters, gravity would do 980 joules of work on it. It has then, and then it will, if we drop it from rest, attain a kinetic energy of 980 joules, which means that due to being at this height, it has the potential, if released, to gain 980 joules. Okay, so we say its potential energy is 980 joules. We drop it and the potential energy reduces to 0. There's a lot more to it. You've got to be careful with potential energy. But that's the basic idea. Okay, well, if we then want to calculate how fast the thing is going when it gets down here, your change in kinetic energy is 980 joules, equal and opposite to your change in potential energy, if you wish. So final kinetic energy minus initial kinetic energy is 980 joules. Initial kinetic energy is 0. So your final kinetic energy is 980 joules, and I threw in then the formula for the kinetic energy, final kinetic energy, and we just solved that for VF. It's very straightforward. We end up something around 14 meters per second, assuming I did that right. And actually looking at it, I'm not sure I did, because we get, no, yeah, it is, it's right. Just a little over 14 meters per second, between 14.1 and 14.2. Okay. The fifth problem throws friction into this situation. Okay, and again, remember I'm using 30 degrees here. If you solve it for 37 degrees, your results are going to be somewhat different. Okay. Without going into a lot of explanation right now, the generalized work energy theorem, where you have work done by non-conservative forces, work by conservative forces, and changes in kinetic energy. Change in potential energy being equal and opposite to work done by conservative forces. In this case, conservative force was gravity. Okay? In other cases, conservative force might be a spring force, or it might be something else. Magnetic force, with that experiment that nobody did for today, because I don't think anybody thought to look at the Friday assignment. Okay. Short experiment. Not going to cause you too much pain. It's kind of fun to do. Okay. You have this relationship. Now we'll explain this more next time when we really talk about the Chapter 7 stuff. Wanted to talk about it today, but only one person got it done. Okay. So the work, okay, this is non-conservative forces. Now gravity is your conservative force acting in this thing. Of course you have normal force, but it's balanced by one of the components of your gravitational force. And it doesn't do any work on this system anyhow because it's perpendicular to the direction of motion. So, the conservative force, gravitational force, is accounted for in your change of potential energy. If there was no non-conservative force, then your kinetic energy change would be equal and opposite to your potential energy change. Potential energy change, since you're descending, is negative, so you'd have a positive kinetic energy, and it would be the situation we see here. We have a non-conservative force now, though, and that's friction. Now, conservative force is path independent. It doesn't matter whether you're descending or ascending, the gravitational force on this mass is always the same. So it's path independent. If I go from here to here, the work done is the same as if I go from here to here along the incline. Friction's not that way. If I slide this thing down the incline, friction does negative work, because the force of friction is this way and my motion is this way. If I slide it, so the frictional force in any case, if I slide down the incline, is in this direction. If I slide up the incline, well, friction's in this direction again. And friction does negative work again. It's not path independent, because in one direction friction points this way, in the other direction friction points this way. So it's a non-path independent force. It's a path dependent force. It's non-conservative. So the non-conservative force, total work done by a non-conservative force, is equal to your change in kinetic plus your change in potential energy. The work done by friction on the system is your non-conservative force. That's equal to change in kinetic plus change in potential energy. You're given that the object attains a velocity of only 8 meters per second, whereas here, when there was no friction, it attained a velocity of 14 meters per second. That means friction did quite a bit to the energy of this thing, the kinetic energy. So, how much work does friction do on the object given that information? Well, change in kinetic energy is 320 joules. Easy to calculate because we started from rest, so the change in kinetic energy is the final kinetic energy. And the change in potential energy is negative 980 joules. We add these up, we find that friction does negative 660 joules of work. If we wanted to go on and calculate the coefficient of friction, or the force of friction, we could easily calculate the force, and then if we calculate the normal force, we calculate the coefficient of friction. How do we calculate the force? Well, 660 joules over 20 meters, right? So we divide 660 joules by 20 meters, and we get 33 newtons. Yeah, okay? So friction exerts a force of 33 newtons back this way as the object slides down the incline. That wasn't asked, that wasn't requested, but we can easily extend this result to that. Then if we calculate the normal force, we can figure out the coefficient of friction, which turns out in this point, in this instance, not to be all that high. Okay, well, those are the examples we started class with. We then went on into the discussion of some of the general principles that we need to understand for the midterm exam in about 10 days, 11 days.